Wednesday, March 25th. This is pre-calc honors. We've just done quadratic formulas. Sorry, quadratic functions. A little bit late at night here, and I've had a very, very full day. I'm in the middle of moving, so bear with me, please. We did something which is essentially completing the square when we put the quadratic into so-called vertex form by completing the square. We didn't finish it and push it all the way to getting the quadratic formula. But since the quadratic formula is one of the most interesting aspects of high school math, I wanted to go over it. Even if you've seen it before, it doesn't hurt to go over it again. Now the problem, if I may say, the problem with high school algebra is that it really doesn't go far enough, because in order to really appreciate the quadratic formula, you've got to go to cubic equations and ask the same question, namely, how do you find a general formula that will express the roots of this in terms of just A, B, and C, the coefficients? Well, you can do that for the cubic form, and maybe you'll say, I'd like to, hoping I have time, I'm not sure if I will, to maybe say something about that. Not today, though. The cubic situation is much more complicated than the quadratic. Now, the quadratic is kind of a freebie in a sense that this was basically known, I don't know, a couple of thousand, 1,000 years ago, something like that. So, first step, here's the derivation of the quadratic formula. First step is to factor out the a. Well, we know that a is not equal to 0, because if a is equal to 0, we just have a line. So we have a times x squared plus b over ax plus c over a, that's equal to 0, and then do the completing the square trick. And this was the key step that people had to understand and be able to do algebraically in order to arrive at the formula. So why does completing the square do it? It just does, and people just found it. They then ask the question, well, if there's a completing the square for the quadratic formula, there must be something like completing the cube for the cubic, and completing the quartic for the quartic, the fourth root, and completing the quintic for the fifth degree. And maybe more about that later. So if we do that, we have this, the a is still outside. We've added the b squared over 4a squared, we've subtracted the b squared over 4a squared, and then we have the c over a. Okay, now, of course, we note that we can factor this as x plus 2b over 2a quantity squared, and leave this term, b squared minus 4ac divided by 4a squared. How do we get that? We combined these two fractions, so this becomes 4a over 4ac over 4a squared. Combine them, and you get this. Okay. Now, if we multiply through by a and put this term on the other side, so this will become a times x plus b over 2a quantity squared equals b squared minus 4ac over 4a. Because remember, we've multiplied through by the a, so the 4a squared becomes 4a. We then divide both sides by a, and we're going to get x plus b over 2a quantity squared equals b squared minus 4ac over 4a squared, because the a goes downstairs. Then we take the square root of both sides. If we take the square root of both sides, we're going to get x plus b over 2a equals plus or minus square root b squared minus 4ac over 2a. Is it starting to look familiar? So that now we subtract b over 2a from both sides, and we get x equal minus b over 2a, plus or minus the square root of b squared minus 4ac, all over 2a. And then we combine these two fractions, and we get the famous quadratic formula of high school: x equals minus b plus or minus the square root of b squared minus 4ac, all over 2a. So it just follows from the same type of thinking that you used in doing the vertex form of a quadratic in order to figure out problems like maximizing revenue and finding the max height of a projectile that was thrown up at a certain initial velocity. The b squared minus 4ac term inside the radical is called the discriminant. The discriminant, did I spell that correctly? D-I-S-C-R-I, discriminant, yeah, that's right. The discriminant can be defined more generally for any polynomial. And it is important. And I don't think, well, let me leave it at that. So we have basically three cases. Notice that we're taking the radical here. There are three things that can happen. The discriminant is greater than 0, it's equal to 0, or it's less than 0. If it's greater than 0, we're going to have exactly two real roots of the quadratic. If it's equal to 0, we get one double root, meaning the parabola just touches the axis. And if b squared minus 4ac is less than 0, we get two complex roots, because we're going to get the square root of a negative number. We don't, well, there are no real roots, but there are complex roots. Simple example. Take the equation 3x squared minus 2x plus 5 equals 0. Calculate the discriminant, easy. Plot the curve. Are there any real roots? And if you want to go further than that, make up a few cases and see what happens. So you've been working pretty hard, and I want to give you a slightly easier day. We'll follow this up tomorrow. Thank you. Bye. Good night.